customer completes checkout and sees a successful payment. Seconds later, the order service crashes. The database contains the payment, but the event that should create the order never reaches the message broker. Support sees a charged customer with no order to fulfill. This is not a rare networking edge case. It is the predictable result of asking one request to update two independent systems. In this video, we will build the transactional outbox pattern from first principles. We will see exactly where a dual write fails, why ordinary retries do not completely solve it, how an outbox makes the important write atomic, and what a production relay needs for safe delivery. We will also cover duplicate events, idempotent consumers, monitoring, cleanup, and the trade-offs interviewers expect you to understand. A typical order service first inserts an order into its database and then publishes an order-created event. Those operations have separate failure boundaries. The database can commit while the broker is unavailable. The broker can accept an event while a later database transaction rolls back. A process can also stop between the two calls. No ordering choice removes the gap because neither system participates in the same local transaction. Follow the failure step by step. Checkout calls the order API. The API commits the new order, so the database now contains durable business state. Before the next line publishes to the broker, the process loses power. When it restarts, the original request is gone. Inventory never receives the event, yet the order remains visible. The system has entered a valid state in each component, but an invalid state as a whole. You might add a retry around the publish call, but a retry loop stored only in memory disappears with the process. Asking the client to retry is also unsafe unless the entire command is idempotent. Even when publishing succeeds, the broker acknowledgement can be lost, causing the service to publish again. Reliable messaging therefore requires durable knowledge of pending work and an explicit strategy for duplicates. The retry decision must survive application restarts. A fragile approach treats publishing as a best effort second step and hopes failures are uncommon. The outbox approach changes the guarantee. Instead of trying to make the database and broker commit together, it stores the intention to publish inside the database transaction that already protects the order. Publishing becomes asynchronous and retriable. This does not create magical exactly once delivery. It creates atomic persistence followed by controlled at least once delivery. Inside one database transaction, the order API inserts the business row and a second row in an outbox table. The outbox record contains a unique event identifier, an event type, the aggregate identifier, a serialized payload, and a creation timestamp. If the transaction rolls back, neither row exists. If it commits, both rows exist. The service can now return success knowing the event cannot be forgotten, even if every application instance stops immediately. A relay process continuously scans for unpublished outbox records. It claims a small batch, publishes each event, and marks successful records as processed. Multiple relay instances can use row locking or skip-locked queries so they do not fight over the same work. Failures stay pending and are retried with backoff. The relay should limit batch size, preserve useful ordering where required, and avoid holding a database transaction open while waiting on slow network calls. Here is the complete control flow. First, the order API commits the order and outbox record atomically. Second, the relay reads the pending record. Third, it publishes the event to the broker. Fourth, the broker delivers it to inventory. If the relay crashes after publishing, but before marking the row complete, it repeats steps 2 and 3 after restart. That duplicate is intentional. Losing an event would be permanent, while consumers can safely detect and ignore a repeated event identifier. The simplest generic consumer pattern stores processed event identifiers. When a message arrives, the consumer starts a local transaction, checks the identifier, applies the business change, records the identifier, and commits. A repeated message finds the existing record and becomes a no-op. Some operations are naturally idempotent, such as setting a shipment status to shipped. Others, such as incrementing balance, require explicit deduplication. The check and business update must share one transaction. There are two common relay implementations. A polling publisher queries the outbox table and is usually the best starting point because it is explicit and easy to operate. Change data capture reads committed changes from the database log and can reduce latency and polling load at higher scale. Tools such as Debezium support this model, but they add infrastructure and operational knowledge. Choose based on measured throughput and latency requirements, not architectural fashion. Monitor the age of the oldest unpublished row, not only the number of rows. A quiet system may have one critical event stuck for hours. Track publish latency, retry counts, failure reasons, and relay throughput. Use a dead letter or review path for poison events that repeatedly fail serialization or broker validation. Processed rows also need retention and cleanup, preferably in small batches, so maintenance does not create long locks or sudden database load. The outbox pattern is not free. Consumers observe changes after a delay, so product workflows must tolerate eventual consistency. Duplicate delivery remains part of the contract. The outbox table grows unless it is cleaned. Ordering is usually practical only per aggregate or partition, not across the entire system. Payload evolution also needs versioning. These costs are worthwhile when a lost integration event would create incorrect business state, money loss, or expensive manual recovery. Here is the complete mental model. Store the business change and its event in one local transaction. Let a relay publish durable pending records with retries. Expect at least once delivery and make every consumer idempotent. Monitor backlog age, failures, throughput, and retention. Use polling first unless scale proves you need change data capture. The outbox pattern does not eliminate failure. It converts an invisible, unrecoverable gap into durable work that the system can observe and retry. Subscribe for more practical backend engineering and system design.